My name is Yongheng again, and I'm working as an associate professor at Aalborg University, Denmark. I'm also the vice program leader of photovoltaic systems. A little bit of information about myself. I did my my bachelor study in China back to 2009, and my PhD study at Aalborg University back to 2014. And since the graduation, and I worked as a postdoc first, then an assistant professor, then an associate professor now at the same department, that is the Department of Energy Technology at Aalborg University. As I mentioned, currently I'm also the vice program leader of the photovoltaic systems research program. And my research focus is, of course, on the grid integration of photovoltaics, power electronics converters design, analysis, control, and how to better utilize power converters or power electronics to integrate photovoltaics. I'm also working a little bit on the reliability in power electronics, because that's one of the important issues in a power electronics-based system. Additionally, I'm also serving as the chair of the IEEE Denmark sections. I'm also an associate editor for several IEEE transactions and also IEEE journals. This includes IEEE transactions on industry electronics, and the IEEE transactions on power electronics, and the IEEE Journal of Emerging and Selected Topics in Power Electronics. I'm also actually the deputy editor of IET, Renewable Power Generation. I'm responsible for solar power generation, including maximum power point tracking. And I was the recipient of the 2018 IET Premier Awards in IET Renewable Power Generation, and I was also an outstanding reviewer in 2018 for IEEE transactions on power electronics. Yeah, a little bit about the university. First, about Denmark. I guess you all heard about Denmark. Denmark is actually a small country in the Nordic region and in northern Europe. And if you are talking about Denmark, the Kingdom of Denmark, typically that's a big country, a large country, as the Kingdom of Denmark usually includes the Greenland, which is the large island in the world, and also actually the Kingdom of Denmark also includes Faroe Islands. So if you're talking about the Kingdom of Denmark, actually it's not a small country. But if you talk about Denmark, usually people refer to this red areas in the northern part of Europe. That's a very small country, and we have around 5 million people across the entire country. And Aalborg University is basically located in the city of Aalborg, which is the largest city in the northern part of Denmark, and it is also the capital of the Nordjylland region of Denmark. But of course, Aalborg is not a big city compared to major Asian cities like New Delhi or Mumbai in India. I think this is quite small, and we have only around 200,000 population in Aalborg. But of course, this Aalborg is almost the third largest city in the country. And Aalborg University has the 3 campuses. Of course, the main campus is in the east of the city of Aalborg, and also we have 2 centralized campus, we can call that one, and one is in Esbjerg and one is in Copenhagen. So in Esbjerg, basically this campus, we also conduct research and education teaching in terms of engineering, but for Copenhagen, and this is mainly focused on social science and business. So they have little research and education in engineering, especially in energy areas. So Aalborg University is quite young. We were inaugurated in 1974, and currently we have more than 23,000 students and 2 23,000 faculty members across 5 faculties in a university. And our university is quite unique because we use this, or we adopt this problem-based learning. We implement this PBL model in our teaching, in our research, and also in the project supervision. So the basic concept for the problem-based learning is that the students are grouped in each semester, then they select a certain topics in this semester. In each semester, then they work on the project, they discuss with their peers, then they solve the practical problems. Then through this problem-solving process, then they learn and they acquire the required knowledge in this process. So that's why we call it problem-based learning. And this is a successful model, at least seen from the experience in Aalborg, because students get really practical experience and they can use those experience in their future work. Even our university is young, but we are performing well, especially in terms of engineering. And according to the US News ranking in 2020, and we were placed as number 6 in engineering in across the globe. And in terms of electrical and electronics engineering, we are number 3 in the entire world. And but of course, in terms of engineering, we are number 1 in the entire EU. So we are really performing well in terms of engineering education and research. So this is the list of best global university for engineering. I snapshotted from US News website, as you can see. For more details, you can follow this link. But anyway, and we are number 6 for engineering, and we are right behind National University of Singapore. That is also one of the best engineering university across the globe. And the Department of Energy Technology, where I'm from, this is actually basically the bird view of the entire campus, Eastern campus in Aalborg. And we have these buildings that belong to the Department of Energy Technology. So we have this one, basically this is for administrative secretaries and also staff members, including professors and PhD students as well. And in this building and this corridor and we have also offices for faculty members and PhD students. But also in this building we have a lot of offices for students, master and bachelor students, because as I mentioned, we use this problem-based learning, and each group, they need to have an space, have an office to discuss with their peers to solve the project. So that's why we provide office space for the semester groups in those buildings. And then also in this building, and also this small building over here, you can calculate as 3.5 large buildings in the department. This is all used for laboratories covering different topics of energy. And this small one, actually it is a building for the medium voltage laboratories. So as I mentioned, Aalborg is a relatively small city, and the main campus to the city center is around 5 kilometers. And one thing is good for the university is that we are building up a new university hospital, which will be affiliated to the Faculty of Medicine when it is finished. And this will be the largest hospital across the Northland region of the country. And this is some daily life picture of the university. But of course, and this is the main campus. This is a picture took from the main campus, and this is a picture from Esbjerg, and this is a picture from Copenhagen campus. But the other thing is, this is actually not part of the university, but it is a must-seen location in Aalborg, according to New York Times listing, and this is actually what we call it Wusun Center to memorize the Danish architecture, Wusun, who designed Sydney Opera. So if you have any chance to visit Aalborg or visit Denmark, I highly recommend you visit this Wusun Center that is have some uniqueness of Denmark, and in particularly some uniqueness of the Nordland region of the country. Anyway, in terms of energy, actually, the Danish government is really pushing the development of renewable energy and the environmental friendly energy, and they have an ambitious plan to reduce CO2 emission. So this is some statistical data from 1990 to 2028, and how the CO2 will be emitted in Denmark in terms of electricity generation. Actually, under the Paris Agreement, actually the new government, the government right now is in charge. The government right now in charge has pledged to introduce decarbonization goals and strengthening its 2030 target to reduce CO2 emission by 70% below the 1990s level, as shown here. The current target, of course, it is 40%. So this is a huge reduction for the government. That's why, and the universities across the country also have devoted a lot of research effort to reduce this, to reach this target. And when you compare the power grid development in Denmark, because we have set this ambitious goal, when you look at the 1985 power grid in Denmark and also 2015 the power system architecture, you can clearly see that we have torn down a lot of central power plants which are based on coal-fired or fossil fuel energy-based power plants, and which were replaced by more environmental friendly renewable energy systems. In Denmark, basically we have a lot of wind power plants that either onshore wind plants or offshore wind plants, as shown in this diagram. So when you compare the power grid in Denmark from 1985 to 2015, the power system has been significantly changing from centralized to the decentralized systems with more renewable energy system in grid. And the Department of Energy, of course, then follow the government policies, and also by its name, actually, we tackle the issues related to energy in terms of energy production, energy distribution, energy consumption, and energy control. So as shown in this diagram, basically we touch all the topics related to energy. For example, as I mentioned, from generation, for example, renewable energy generation and also conventional generations, but also we have the application aspect, like industry applications, commercial applications, all the areas related to energy. And we have colleagues working on those topics. But what you can see from this diagram is that power electronics is one of the important part in this energy transition and energy utilization, not only in Denmark, not only in Europe, but across the entire globe. Anyway, the Department of Energy Technologies organized into different sections, and we have colleagues working on electrical machines, conventional power systems, and also power electronics, also other topics related to thermal energy, thermal fluids. And as I mentioned, we have another campus in Esbjerg, and there are also energy activities in terms of research and education. So down to the sections, we organize a department in terms of research programs. One of the primary objective is to synergize different research efforts into different sections into one joint forces to address the current challenges. The other thing is that we could define and follow different research topics that is emerging across the globe. So Basically, there we have different topics. For example, efficient and reliable power electronics, wind power system, photovoltaic systems, and all the other research programs. And as I mentioned, because power electronics is one of the key components to energy conversion, and we have the primary manpower around 60% manpower is in power electronics and its applications. So in the department, we have more than 40 faculty members, more than 100 PhD students, and the other important thing is we always welcome visiting scholars and students from the globe. So basically, if you wanted to visit us, you are very welcome to contact me. Yes, about the technical talk, and today I'm going to walk through this active power control of photovoltaic systems for frequency support, basically how we can better utilize active power to provide and to support the power grid in terms of frequency. And in this talk, first I will brief the development of PV systems with also general information of some general information of renewable energy systems. And then I will present the demands of solar PV inverters, and because we have a high penetration of PV systems, what are the demands seen by the system operators. Then the focus will be on the flexible active power control, how we can better control the PV system in a way to provide frequency support. Then I will present some examples and how we can really implement the frequency support by controlling the active power from PV systems. Then at last, I will summarize the presentations, and of course, we can have some time to discuss, and I will be glad to answer any questions you may have. Yeah, in terms of renewable energy development, we know that the global renewable energy has experienced a significant increase in the past 2 decades. And this diagram basically summarizes all the types of renewables from 2000 to 2019. As you can see, the total capacity for renewable has increasing as in an exponential way. And by 2019, the total capacity has reached 2,500 gigawatts across the globe. But of course, as you can see here, still hydropower is number one. But the total of wind and solar is almost equal to the hydropower, and in the near future, and the wind and solar energy will exceed the hydropower in terms of renewable installation capacity across the globe. Anyway, and when you compare the net total annual additions across the globe, we see that from 2000 to 2019, actually, we have added much more renewables compared to the non-renewables. And one of the things, of course, then we still want to address the issues related to energy crisis. The other thing is the environmental concerns, and we have to reduce the non-renewables instead of then add more environmental friendly renewables. So the other thing is behind the increase of renewables is that the cost is declining. For PV, for example, panels, cost is declining very fast. And in terms of PV technologies, first let's walk through a little bit the PV cell technologies. This is the diagram from Nestor Renewable Energy Laboratories, and back to 1970s. Then you see that the PV technology, cell technologies, has also emerging and evolving very fast, and in terms of efficiency, it has been increased significantly in the past a few decades. And this is also one of the driving forces then why more and more PV panels are utilized in electricity generations as the efficiency is increasing. And yeah, as I mentioned, our solar PV capacity has experienced an exponential increase in the past 2 decades, and this diagram basically shows the increase by years. And one of the conclusions we can draw here is that the solar energy is catching up with wind in terms of the installation capacity. So until 2019, the total installation capacity across the globe is almost 600 gigawatts, and the single year of 2019, there was 100 gigawatts solar PV installed across the globe. So as I mentioned, one of the driving forces behind is that the efficiency improvement of solar cells, and the other thing is the declining price of PV modules in terms of manufacturing and installations. So, and when you compare the growth rate, then with other renewable energies, actually solar PV has the fastest growth rate between 2018 to 2020, and then we could anticipate that in the near future, solar PV energy will be the #1 in terms of installation capacity among the other renewable energy systems. And furthermore, as I mentioned, the cost of the PV cells itself, or PV modules, are still reducing. The other thing is, if you look at the entire PV systems, then we further need to reduce the cost of energy in a way to make the PV systems more competitive compared to the other renewable energies. And this is the cost of energy requirement published by the Department of Energy as the Solar Energy Technologies Office. This is a Sunshot initiative, basically defined the levelized cost of energy according to different types of PV technologies. For example, for residential applications, for commercial applications, and for utility scale applications. As shown in this diagram, actually for utility scale applications, and we have reached the 2020 goals, that which means the cost of utility scale PV system is right now below 6 cents per kilowatt hours. So this is an amazing achievement. But of course, there are much more efforts we should make in order to further reduce the cost of PV energy. So we have talked a lot regarding the development of PV and the development of renewable energy, and also the government policies seen from the Danish government. But how do we really integrate solar PV energy? This diagram basically summarizes the general power conversion of photovoltaic systems. Basically, it includes 3 parts. First, of course, that's the photovoltaic effect. That's the generator side, and then the PV power generation is based on the photovoltaic effect. And this gives you the DC power. And the load here we are talking about, that's power grid. So which means you wanted to connect the DC power to an AC power grid. Then in between, then you have to use electrical power conversion devices. Basically here you can use power electronics. So which means the power electronics are essential to realizing the power transfer from solar PV to the electricity grid. And the other thing is, as I mentioned, because the solar PV generation is environmental dependent, then one of the things when you use power converters, you have the possibility to really optimize the power generation from the solar PV unit in order to maximize or optimize the energy production from the solar PV panels. For example, if we are looking at a cloudy day and there are passing clouds, then this will create some challenges to your systems, because you are continuously operating the systems as the maximum power point tracking. What you see at the grid side is also a highly fluctuating power that is injected into the grid. So this is not something we want, because when you consider the generation and the demand balance, because you continue injection of fluctuating power, and you may cause voltage fluctuation and also frequency and instabilities because of unbalance between the generation and the demand. Another example is that, as I mentioned, power electronics is important to integrate photovoltaic systems with the grid. And the power electronics, actually, it is a static conversion device, and there is no physical rotating mass in power electronics. So in that sense, if we continuously replace the conventional synchronous generator, which is used to govern the system, the power system frequency, then we see that the inertia of the entire system is reducing. This is an example from National Grid UK, as they have studied then from 2010 to 2013, then how the system inertia is reducing. Actually, the system inertia is something that's related to the frequency stability. Well, you have a low inertia in the system, then when there is a frequency events, then the whole system may not be able to properly respond to the frequency event, then you may experience a huge power loss or generation loss in the entire system. So with the above, then we require our PV systems to be grid friendly, because we further want more PV energy into the grid. Then how to define grid friendliness? In my opinion, and if you are talking about the grid-friendly PV system, where the PV inverters should be able to modify the power profiles and to support the grid if needed. And the other thing is that your PV inverters should be able to respond autonomously to voltage and frequency demand, and also to respond to communication signal if necessary. So this requires our PV inverters to be multifunctional, and this can be achieved through the design and the control of PV system. Today we're gonna discuss, or we're gonna walk through how we can achieve the control, how we can achieve frequency support through the active power control. The other thing is as the photovoltaic conversion is a multi-stage conversion systems, that there are various demands at different stages in order to make the system to be grid friendly. But of course, there are some general requirements, for example, like power optimizations, the controllability of the converters, the power quality issues, and also the other supportive schemes, as I mentioned, for example, frequency support and voltage support and inertia provisions, considering the high penetration of PV system. And actually, the only control plant or the control unit in the system, of course, is power converters, which means all the demands should be met by properly controlling the power electronics in PV systems. And this including the basic control as well as advanced grid supportive schemes, as I mentioned in the previous slides. So in this presentation, we're going to focus on, and we will demonstrate how we can achieve flexible active control and in order to provide frequency support to the grid. And in the past, basically, the penetration level of PV systems is not that high. And in that respect, the generation from the fluctuating generation of PV system, actually, it won't cause significant impact on the grid stability. And at that moment, PV systems are required to maximize the power generation from the PV panels, which are dependent on the solar irradiance level and also ambient temperature. But nowadays, because of the penetration of PV systems are increasing, and also the power rating of a single PV unit is also increasing significantly. And under these circumstances, we could not operate the PV system always in the maximum power point tracking mode. Instead, there are much more flexible active regulation requirement. For example, your PV system should be able to curtail active power when it is demanded by generating constant power to the grid. And your PV system should also be able to provide power reserve when there is a frequency support needed. Then your reserved power can provide this frequency support. And the other thing is when your PV power is fluctuating very fast with faster dynamics, then this is not desired. Then we have to control the ramp rate of the active power in order to maintain the frequency stability. So with the above requirements, then we would introduce the flexible active power control for PV systems. Of course, and the first solution comes to my mind is that we integrate the storage units in the PV systems, and this is a very effective and flexible way. When there is extra power, then you wanted to discard, then you can put this power to the storage systems, and also when there's extra power needed from the by the grid, then you can provide the support or provide the extra energy from the storages. So this is really effective and flexible. But of course, because you have new other additional hardware required, then this will inevitably increase the overall cost and also the control complexity of the systems. And the other drawback of this solution is that the power electronics and the energy storage technologies are two life-limiting components. So when you put this on in the entire PV systems, the entire system reliability is affected, and the lifetime is challenged of the entire system. And another solution is to use dynamic controller loads, and this is a very cheap solution, but it is not very flexible because when there's excessive power need to be taken care of, then this power can be dissipated on the dummy loads. But if there's additional power required by the grid, and these dummy loads cannot provide extra power, so that's why it is not flexible. And another thing is this also involves hardware modifications and investments, so the control is complicated, and also the cost is also a little bit high compared to the original systems. And another solution is to switch multiple units in the systems, as illustrated in this figure. Actually, this is very limited by the system configuration, and it is not flexible. And the control is also very complicated, and it relies on the communication in the systems. And another important issue is that when you switch in and out a lot of units, you may challenge the stability of the entire system, as well as the individual components, of course, but the entire system stability is challenged. And another drawback for this solution is similar to the previous solution, is that it is an unidirectional solution, which means when there's additional power or energy required by the grid, your system cannot provide additional power because it is limited by the maximum available power from the PV units. So with the above reviewing of the solutions, potential solutions, then we propose this flexible PowerPoint tracking solutions. The solution does not require hardware modifications, and it is easy to implement, and also it is universal to all the PV units because it only requires software modifications. And the basic concept is that you move the operating point of the PV system from the maximum power point to the non-maximum power point, reduce power mode, in order to address the power regulation issue. And of course, this has a drawback, that is that the system cannot provide extra power, which means this solution is also unidirectional. And this diagram basically illustrates how the system is operating with flexible PowerPoint tracking. As I mentioned, basically the idea is to move your operating point from maximum power point to flexible power point, either on the left-hand side or the right-hand side. Then you can reduce the power generation from PV panels, or the power, you can regulate the power from the PV system. Yeah, the first active power control solutions we wanted to discuss is this constant power generation, which is also referred to as power limit control. So the basic concept is that, or the requirement is that when the PV system has a power limit demand, and when the available power is below this demand, your system should operate as a maximum power point tracking mode. While when the available power is higher than this limit, then your system should output or should generate a constant power that is equal to the power limit, as illustrated in this diagram. So in order to achieve this control objective, there are also three solutions. The first one is you can use this direct power control, as illustrated in this diagram. So the concept is very simple. Then we have the maximum power point tracking block. Then it gives you the power reference. Then you add a saturation block, sort of to limit the power from the MPPT calculation. Then according to the power limit, then you send this a new reference to control your power converters in a way to realize this power limit. And another thing is another solution is that you can use this current limiting scheme, as illustrated in these diagrams. Then you under different solar irradiance levels, and when you set a current limit, actually you can also limit the power indirectly, as illustrated in this rectangular shape over here. And the implementation of this current limiting scheme is also simple. Now we have the maximum power point calculation block diagrams, which gives you the current reference. Then based on the power limit, you calculate the current limit as the limit of the saturation block, and this will limit the current reference, and it gives you a new current reference for your converter. Then you can control the converters to achieve the power limiting. And the current limit is calculated according to this equation over here. And the third algorithm is the flexible power point tracking algorithms, as I mentioned. And the algorithm is to modify the maximum power point tracking algorithms. When it is below the limit, then the system operating at the maximum power point, and at certain time instant, the irradiance increase, then your PV system should operate at the flexible power point tracking mode. Then either you move the operating point to the left-hand side or to the right-hand side. So one of the observations from this figure is that if you operate at the left-hand side, the distance is far, which means your dynamic is slow compared to the right-hand side. But the other thing is the slope on the left-hand side is lower compared to the right-hand side, which means the steady state performance is better on the left-hand side. And this figure basically shows the implementation diagram, block diagrams of this flexible power point tracking algorithm in order to limit the power from PV generating systems. We have done some tests in order to verify the above solutions, and we also consider different power limiting levels. And here we use a trapezoidal solar profile as shown here. And this is the dashed red line is the solar the available power. And as I mentioned, we apply different power limits. And the first one, the top figures refers to the control algorithm using the direct power control. As you can see, we can limit the power at the required level. And the bottom figures show the schemes using the current limiting algorithm. So basically, we can also achieve the same control objective. And then when we apply the flexible power control point tracking algorithm in order to limit the power generation, we can achieve the similar performance. And as I mentioned, there are two operating points corresponding to the same power limit. And either you can operate at the left-hand side, as shown in this diagram, or the right-hand side of the maximum power point, as shown in this diagram. And as I mentioned, because the slope on the left-hand side is smaller, lower than the right-hand side, so the left-hand side has a better performance in terms of steady state, while its dynamic is slower compared to the right-hand side because the distance is farther than the right-hand side. Anyway, the three control objectives can achieve the three control measures can achieve the power limiting control effectively when there's necessary. And also, we have done the test considering real practical environmental conditions. We consider two daily profiles. The first one is a clear day, and the second one is a cloudy day. And the rated power is 3 kilowatts, and we limit it by half at 1.5 kilowatts, as shown in this figure. Basically, when we apply the flexible active power control, these flexible power point tracking algorithms under both environmental profiles, we can achieve the power limiting control effectively. And the second active power control strategies I would like to introduce is this power reserve control. So why we need this power reserve control? The requirements is put forward because of considering the grid stability due to frequency excursions, and the basic idea is to use the reserve power to achieve frequency-dependent active power control and to regulate the frequency. So power reserve, and in this sense, the power should be reserved, and in case of there is a frequency regulation required, and the PV system can release the power in order to support the grid in terms of frequency regulations. Again, here, in order to achieve the power reserve, we can also use this flexible power point tracking algorithm, but here, the power limit is not a constant anymore, but it is a dynamic changing power limit according to the available power as defined in this equation. And this diagram shows illustrate the operating principle of the power reserve control by using the flexible power point tracking algorithm. Supposing the system is operating at the maximum power point under 500 watts per square meter irradiance level. Then when we receive the demands to operate at the power reserve mode with an amount of reserve power equals to delta P, then the system will move to the flexible power point 1 as required to reserve this amount of power. When the solar irradiance changes, then we estimate the available power, then we reduce the power with the required amount of reserve, then we operate at this point. And when the irradiance change again, then we operate at this point in a way that we achieve the power reserve as shown in this, as illustrated in this diagram. Here, then it comes to questions. Then the first, then it comes to one question is the one challenge is that how to measure the available power. And of course, and then you can either install a solar irradiance measurement to measure and to forecast the PV array and in a way to estimate the available power, or you can use artificial intelligence method to predict the maximum available power, and also you apply curve fitting method to predict the available power, and all those solutions, either it is model based or it requires additional hardware equipment. So which means it will increase the cost, or it is not reliable when the PV panels degrade. So with the above concerns, now we would like to introduce two methods. The first one is what we call it master-slave power reserve control strategies. Basically, we employ a small PV unit to operate in the maximum power point tracking mode, and they use output power to approximate the total available power of the entire systems, and in a way to operate as a flexible power point tracking mode in order to reserve the power. And the second method is what we call it sensorless power reserve control. And the concept is to adopt a hybrid operating mode between the maximum power point tracking mode and the power reserve tracking mode in one single PV unit. Then we can achieve the power reserve as demanded. So for the master-slave power reserve control, it is applicable to multi-stream PV systems with multiple PV panels, as illustrated in these diagrams. Now we have multiple PV units connected to the DC bus. Then we use a string inverter to connect it to the grid, as illustrated in these diagrams. So how to implement this power reserve control? Then we use a two system to illustrate this concept. As I mentioned, one of the units or some units are operating as the master streams. They operate in the maximum power point tracking mode, which gives the available power in real time, as shown in these diagrams. That this available power information is fed to the slave strings or slave units, as shown here, then which is subtracted by the reserve power requirement. Then we generate the power limit. Then we can control the slave strings or the slave unit operating as the flexible power point tracking. Then the output power will be something look like this one over here, and with a certain amount of reserve. Then when you look at the total power to the grid, is something like this one, the figure showing in the middle, which also has a certain amount of reserve as expected. And with this control algorithms, we have also done some tests. We consider two daily profiles on two string systems, and the power reserve here we consider is 200 watts. And as I mentioned, we use one PV unit to operating as the master unit, which is PV1, and the continuous method available power. And then the PV2 is operating as a slave string, and which is operating as the power reserve mode. Then what you see at the grid side, the total power will be something. We will be in a profile with a certain amount of power reserve, as illustrated in this figure. So we have done the test under a clear day profile and also clouded day profiles. And basically, both operating profiles and can achieve this power reserve as demanded, especially in a clear day, then we can relatively accurately to achieve the power reserve. While for cloudy day, it's a little bit challenging because the measurement is also challenging. Even you operating as a maximum power point tracking mode, the output power is also challenged under cloudy day, as shown in this figure. Anyway, that was the master slave control to achieve power reserve control. Another solution is based on this sensorless power reserve control. So the concept is to routinely operate the PV system at maximum power point tracking mode to estimate the available power. Then later on, the system can operate in a constant power generation mode. Then what you see at the grid side will be a power profile with a certain amount of reserve. This control strategy actually it is similar to a digital sampling concept, and as illustrated here, then we routinely operate the system at maximum power point tracking mode. Then we quickly jump to the reduced power mode with this amount of power reserve, and then you can achieve the control objective. So basically, this gives you the control algorithm of this one. As I mentioned, it's similar to the digital sampling techniques, and here then we continuously operating. This gives you we first routinely operate the system at the maximum power point tracking mode to estimate the available power, which is subtracted by the power reserve. Then we update the power limit. Then you can achieve the control. However, there's one of the issues related to that one is that even we use a very short period to estimate the system available power by operating at the maximum power point tracking mode, and this short period will generate excessive energy. Then this energy should be taken care of properly, otherwise you will see power pulses at the grid side. So what we do here is that we store this excessive energy at the DC link, which means we allow the DC link voltage to increase in a way to store this energy due to the routinely operation of the maximum power point tracking control. So this figure basically shows how we can implement this power smoothing control in a way to store this excessive energy. And with the power control, and this figure shows how the power will look like at different stages. For example, at the PV side, then you will see some profiles like this one with spikes, and while you see at the grid side will be something like this one more smooth, because you store the excessive energy at the DC link, which means the DC link voltage will go up and down because of the routine operation of the MPPT control. Yeah, and for these algorithms, we have also done some experimental tests. And the first one is we consider a constant irradiance condition and temperature condition. And this is here we consider the power reserve of 500 watts, as shown here. Then this is the PV voltage, how it looks like. And we can operate at the maximum power. Then we quickly jump back to the reduced power mode, which means the PV operating voltage is lower than the maximum voltage of the PV systems. And this figure shows how the DC link voltage is looks like. And as I mentioned, because we need to store the excessive energy due to the MPPT operation, so we have DC link voltage increase and decrease. Anyway, then the red line is the available power, and this the blue line are the PV powers, as you can see here. And we operate at the maximum power point, and we operate as a reduced power mode. and what you see at the grid side is something with a power reserve of 500 watts. And we also test the systems considering changing in condition, and we have a ramp up solar profiles, and this shows the PV voltage, and this shows the DC link voltage. As you can see, the voltage is going up and down because it has to store the energy. And the blue line here is the available power for the PV systems, and the purple lines are the power sent to the grid, and in between that's the real PV power. And anyway, and when you compare this one, we can successfully reserve an amount of power around 500 watts, as shown in this diagram. Yes, that was about the power reserve control. And then the last active power control strategy we would like to introduce is this power ramp rate control. So the requirement on the power ramp rate control is also to consider the stability challenge due to fast power fluctuation. And then we have to limit the power fluctuation in order to limit the frequency variations indirectly. And there are two tasks in order to achieve the power reserve control. First is how to measure the ramp rate, and the other one is how to achieve the ramp rate control. So in terms of power ramp rate measurement, we use the most common way, that is we use a running window. Then we measure the power difference in this window, which is divided by the window length. Then we can obtain the ramp rate. Then we use this ramp rate, and then we compare this ramp rate with the requirements. And if it is below the requirements, then we continue to operate the system as a maximum power point tracking mode. And if it is higher than the ramp rate, then we sort of reduce the power in order to reduce measurement, which means that the system can still achieve the ramp rate regulation based on this flexible power point tracking algorithm. This slide basically shows the operating principle of this power ramp rate control based on the flexible power point tracking algorithms. As I mentioned, if the ramp rate is lower than the limit, then we continue to operate at the maximum power point tracking mode. When the ramp rate is larger than the requirement, then we sort of reduce the output power, then we reduce the ramp rate then in order to meet the requirement as shown in this figure. Yes, with this flexible power point tracking control, we also did the experimental test, and then we considered two profiles with different dynamics. And the first one is slow dynamics. Then we have this trapezoidal available power. Then we control the ramp rate as 10 watts per second and 20 watts per second. And for the faster dynamic profiles, we also control the same thing. And as you can see, we can basically achieve the control objective as required. And this slide shows the controlled ramp rate, the measured ramp rate of the systems. As you can see, for the slow dynamics, we can control this one as required, and for the fast dynamic, it is just a little bit challenging. But anyway, we can also achieve a similar or satisfactory control of the ramp rate of the PV system. And furthermore, we did the test under two daily profiles, the clear day and cloudy day. Here we control the ramp rate at 10 watts per second, and for the clear day and a cloudy day, as shown in these diagrams, for the clear day, it is very easy to control at the required level. And for the cloudy day, that's a little bit difficult because you have a large variation in the power output. And anyway, and in general, we can achieve the control objective of the power ramp rate limit. But an interesting point is that for the ramp down rate, actually our solution cannot achieve this regulation. We can only control ramp up limit control, because we can only reduce the power from the PV systems. While for the ramp down rate control, you have to provide extra power to the systems, and this can be done either using energy storage systems, or you can combine the power reserve control with the power ramp rate control in order to regulate the ramp down rate of the systems. Yep, the above was about the flexible power control for PV systems, and as I mentioned, the active power control, basically one of the objectives is to achieve a frequency support of the PV systems, and by providing inertia to the power grid, then how this looks like. And when we look at the PV curve of the power and voltage curve of a PV system, it is something like that one. When we operate the system with a certain amount of power reserve, either at the left hand and or the right hand side, actually this gives you the possibility to tackle the over frequency issues and also the under frequency issues. So for the over frequency issues, then you can further reduce your PV generation power, and it will sort of reduce the power generation from PV system, then the lower frequency can be tackled. And in terms of under frequency issue, then you can provide extra power to bring the system frequency back to the nominal conditions. So which means the power reserve control can provide the frequency regulations as required in power grid. And the other thing is when we look at the system damping, then this is also related to the power. And for the virtual inertia, actually, it is in proportion to the derivative of the frequency, which is the Rokov defined rate of change of frequency. And while for the frequency damping, and this is related to the frequency deviations. So both are related to the active power control of the systems, as shown in these diagrams, then how to better coordinate the power reserve in order to meet those two requirements. That is something of interest. We have done some studies how to coordinate and how to implement this one over here. Then this is the PV power output power when this is power reserve. Then this is the power to the grid. When we have this virtual inertia control, you can see that the frequency, the rate of change of frequency is lower compared to the system without virtual inertia control, and the frequency nadir is also improved when we use the virtual inertia control by controlling the reserved power from PV systems. So this basically demonstrates that when you have the reserved power, you can regulate the frequency. You can adjust the frequency of the PV system. And the other thing is, as I mentioned, for the PV systems, you have to coordinate the active power control in the systems, and this slide basically shows the requirement or the indices of frequency events, frequency indices of power systems. When there's a frequency events, then first the frequency will drop and to a lower level, what is called nadir, and the duration between this one, what we call it rate of change of frequency. Then in this period, then we apply the primary frequency control, which is sort of trying to stabilize the frequency of the systems. And at this moment, then a secondary frequency control should be enabled in order to bring back the frequency to the nominal range as required in the system. So this is basically the frequency control in power system. That there are some points or some parameters that we have to consider in the implementation of the control. That is the nadir, the rate of change of frequency, and the steady state frequency, how large that is deviate from the nominal condition. And here there are also some requirements for those parameters. For example, the Rohloff withstanding capacity. That is this is a grid code from the Northern European grid, and that for the Rohloff withstanding capability, that's around plus minus 2.5 hertz per second. And then this with the above requirement, then we should optimally utilize the power reserve of PV systems, and then we can also adjust adaptively the inertia constant and damping gain in order to meet different requirements. For example, the Rohloff, the nadir, and also the steady frequency deviation. And we have done some analysis in terms of different inertia constant and also damping gain for the systems, as shown in these diagrams. When you change the inertia constant and also the damping gain, when you have a large inertia constant, basically the frequency nadir will be larger. And when you have a large damping gain, basically the frequency nadir is also higher. But the interesting point here is that the steady frequency is also higher, close to the nominal frequency. So which means we would expect a large damping gain in the steady state, while at the beginning we expected a higher inertia constant, as in this figure. In terms of Rohloff, as mentioned, because you have a larger inertia constant, so the Rohloff should be improved. And while for the damping gain, then this is basically has not so much impact on the Rohloff at the beginning. So with the above analysis, then we can conclude that large inertia constant before the frequency nadir is necessary, while after the frequency nadir, then we expect a larger damping gain in order to minimize the frequency deviations. So with these considerations, so we proposed control strategies to coordinate the control or coordinate the utilization of the power reserve in PV systems. And this is we also compared the strategy with other control schemes, with frequency control and without frequency control, with fixed inertia constant or with fixed damping gain, as shown in this figure. Basically, when we adopt the proposed method, because we implement a large inertia constant before the frequency nadir, as you can see here, we can basically achieve the same performance in terms of Rohloff as the other strategy, while after the frequency nadir, we implement a larger damping gain, which means we can bring the frequency as much close to the nominal condition as possible, as illustrated in this simulation studies. Anyway, and with the control, with the proposed control, and we can achieve lower Rohloff, and also we can achieve a higher frequency nadir, and the recovery frequency is higher compared to all the other strategies. Basically, the proposed control performs well in reducing Rohloff and the instantaneous frequency deviation, as I mentioned. and it optimally utilizes the power reserve to reduce the steady state frequency derivation. So, which means it is a promising solution to implement in a PV system to improve its grid integration performance. Yes, that was all the technical presentations today, and I hope you enjoyed the presentation. And basically, all those materials are based on the 2 books we have published. And one is Advances in Grid Connected Photovoltaic System Power Systems, and you can take a further look in this book. And the other is Renewable Energy Devices and System with simulations in MATLAB and ANSYS. So there are also examples that you can look at. Yeah, basically all those materials were generated from the project, what we call it PV2 Grid, and this was sponsored by Solar Area Net Scheme through EU, and in the national funding agency was EnergyNet.dk. So we would like to acknowledge all those funding agencies, but of course also some materials from these presentations are from Professor Fred Bobia, Dr. Aria Savanich, and my PhD student, Ms. Qiaopen. So I would like also to thank them for providing the materials. Yes, to summarize, and we know that PV is still booming areas, and PV is still one major renewable energy resource, and its installations are still increasing. So power electronics is the key to this efficient and reliable PV power converters. So in the future, we will expect much more PV system in the grid. And of course, the high penetration degree will challenge the power grid in terms of stability. And in order to further increase the penetration degree, then we have to implement grid-friendly control strategies as introduced in today in this presentation. For example, active power control, including power ramp control, power limiting control, delta power control. And through the control, we can effectively resolve the issues and to address the challenges due to high penetration of PV system. And again, I would like to emphasize is that power electronics is the important part to the integration of the solar PV energy. And advanced design and control of more power electronics in PV system will enable a higher level manageability of PV system and the entire power grid. Yeah, with that, I would like to conclude this presentation, and thank you for your attention. And I hope I can join the Q&A and to discuss with you. Otherwise, you can just send me an email, and I would love to discuss with you for any issues that may arise during the presentation. Thank you again. I hope you enjoyed the rest of this webinar and all this workshop. And thank you so much. Take care.